Good evening, everyone. We will be getting started with our talk on symbolic execution in just a minute. Just as a heads up, this will be the last talk before Thanksgiving break. Next week, we won't be having any talks, so just a heads up there. Let's get going here. So, this Monday, we talked about Z3. And as you might recall, Z3 is a theorem prover, which lets you solve, systems. So things like, maybe math problems or logic problems, that kind of thing. It lets you declare variables, put constraints on them, solve the system, and either get concrete results or get proof that there is no answer. So Z3 is very useful for finding solutions to complex systems. Like, for example, the kind of chain of logic that makes up, crackme and reverse engineering challenges. In case you're unfamiliar, kind of crackme means it's a program that they want you to try to find the secret in it. I think the kind of name comes from cracks of programs where they uh, found how to get the license key, that kind of thing. So same idea, extracting secrets from programs. So this theorem proving is quite important for something called symbolic execution, which is a kind of new and very radically different way to think about actually running a program. So to define symbolic execution, we're actually going to start with its opposite, concrete execution, which you'll probably be very familiar with, because concrete execution is just the process of running a program and observing its what happens. So all those inputs combined with the actual code of the program will uniquely determine its result. So if I put in 10 to a program and it does something, it should do that every time, assuming it has no other inputs. And that gives us a trace. And so you might hear like, well, we have execution traces, we're analyzing that. So that's what that entails. And we can perform dynamic analysis on a program as it runs, so we can see, okay, what functions are being called, what order does it happen in, what are the hotspots, that kind of thing. So for example, this program here, we'd ask for the password. We give it a password. It says no. Great, that was concrete execution right there. So the program that we just ran there looks like this. It scans for input, gets a number, and if that number equals, leap, it prints correct. Otherwise, it prints no. And when we ran the program, obviously, input was set to 1,000. 1,000 does not equal 1337, so it took the false branch and printed no. Extremely obvious, I think. But let's look at this in a different way. And I think we've already covered this, the concept of the basic block, but we'll just have a look at that again real quick. A basic block is just a sequence of instructions that runs uninterrupted. It goes from the start to the end, nothing can possibly change its path, and at the end, something happens. So for example, this is the kind of basic block representation of that program. We read the input, we say, okay, does it equal leap? If so, we take this branch. If not, we take that branch. And when the program executes, we say, okay, X is 1337, and that I picked the wrong. That should be any number other than 1337. That's my bad, because I want to take the false branch here. Say it was 1,000, we would go to the false branch and say no. How silly. Anyway, flubs aside. So in this case, we could probably just reverse engineer this ourselves real easily. We look at the branch and say, okay, it says, does the number equal this thing? If so, take the branch. That's pretty obvious. But what if it's a lot more complicated? Like, what if it's a whole bunch of XOR operations, or it's some other weird kind of keygen thing, I don't want to deal with that myself. I want the computer to do it for me. And that's where symbolic execution comes in. So it's a different way of thinking about this. Rather than looking at specific values, we're kind of looking at, constraints and variables. So, for example, I want to get to that correct block. And obviously, to get to the correct block, I need to take the true branch. And to take the true branch, I need to pass this test. And to pass this test, x must equal, what's on the right side. Therefore, the input must be 1337. So that's kind of the reasoning going on here. We're looking at constraints and variables, not specific values, and this can go both forwards and backwards. There's different flavors of symbolic execution, kind of depending on which way you approach a problem. And so constraints can be, this number is greater than 100, or these two things are equal, or life is pain, or what have you. Now, once we have those constraints, we can ask Z3 to solve it. And so that, we will just kind of build up these constraints and then say, okay, Z3, can you find me a configuration that satisfies this? Now, obviously, it gets a lot more complicated than X, equals Y. We have, program semantics. We have all kinds of stuff going on here. But at the kind of fundamental level, that's what this is. So let's give this a try. If you look in the video description or copy the link slides here, we have a quick demo whipped up. It's just a couple C files, which you'll compile in a minute. And you'll also want to be on the virtual machine because we've already set up angr for you. And angr is the symbolic execution engine that we're going to be using here. So once you fire up your shell, if you just run source angr bin activate, you'll get a terminal here. And we have a look here. Just go back to my home directory, fire this up, and now we've got a virtual environment loaded. You see we have this little angr here. And this means when I pop open a Python shell, I'll have the angr libraries available. If I didn't have that imported, didn't have that activated, this should, it does work. Oh, I installed it globally too. You'll want to be using the virtual environment anyway, though, just because that'll make sure it's set correct. Let's see here. Anyway, source angr bin. I think we installed 2 copies of it. You'll definitely have it in here. There it goes. Yeah. Oh, you know what? When I said import angr, I imported this directory. That's what happened. So yeah, you want to have the virtual environment ready to go. And once you have that here, we'll have the entire angr library ready for us. So, where is my slides? There we go. So you just want to pop into the challenge directory and build the challenges, and then open your Python interpreter up. And you'll see it'll produce a few programs called like easy, medium, hard, and painful. So the first step with angr is loading up a project. And the project basically tells us, it has everything about the program. It stores, what it is, where it is, what kind of architecture it's using, that kind of thing. And it's where we'll get everything else from. So you see here, I just loaded up the easy program and checked, okay, it's an AMD 64 program. I hope it is. I just compiled it. So the way angr works is it keeps track of specific program states. As execution proceeds, it will, keep track of all the, the specifics of what's going on there. So it keeps track of registers, it keeps track of the stack, it keeps track of everything. So we can ask it for the entry state, which is the kind of, that's the state of the program the moment you begin execution, before anything happens. And if we have a peek here, we say, okay, RAX contains, 1C, and RIP contains the instruction it begins on, because remember, RIP is the instruction pointer in a 64-bit program. So that, we can see here that it is modeling everything. So what we want to do here is we want to simulate execution, kind of walking forward, seeing what will happen as the program runs, and what decisions does the program make. So we can just ask the project to give us a simulation manager, and that basically it's a big bag of states that kind of intelligently picks the right one to try advancing at any given time. So if you ask it for the simulation manager from the starting state, you'll see that we begin at this kind of this entry state, and then as we take steps, it'll tell us how many different paths it's currently trying. So here I took a step and we have 1 active state. And you see it has moved. It went from 40, 10, 60 to 52, 60, 50. And we can tell it to keep exploring for a while, which will get really painful for large programs, but it is perfectly doable for this small thing here. So if I tell it to explore, it will just run until it runs into dead ends. And a dead end is something where the program has stopped. So if I run that, I can actually then see what the program did in those two different cases. So in case 0, if I look at standard out, the posix.dumps function here will just give us standard in, standard out, whatever, and it'll say, okay, do you give me the password? No. Or can you give me the password? Correct. Now you can imagine that if we had tons and tons of possible results, this would be a bit of a mess. I don't want to dig through each one of these possible paths myself. So what we can do is ask angr to only look for paths that take us where we want to be. And you remember the program prints correct if we get it right, and no if we get it wrong. So what we can do is tell it, okay, you're going to do is explore, but you're going to be looking for something that matches this predicate. And all this thing does is says, does this state have the word correct somewhere in its standard output? So that means that when we explore, we'll hit a single state here that actually matches our find function. And if we ask for it, we'll get a state. And again, so the simulation manager is just there to kind of organize things for you. I believe as you could do this manually, but it'd be terrible. So it keeps this list of things it's found, things that have dead-ended, things that are still alive, that kind of thing. And if we just ask it for standard in, we get leap. And standard out, as expected, contains, correct. So therefore, we found the only input that results in the program printing correct. And we can actually search for the opposite too. We could say, give me a state where the program doesn't print correct. And the result is no input. It will find something that satisfies your condition. And I think actually it might not even run the program, because at the start there is nothing in the output. But you can see here we can kind of filter for different outcomes. So that was easy.c. Medium.c is very similar. It just got some extra math involved. We have a look here. If we have a look at medium.c, we'll see it's just got a little bit of math here. It's like input times 2 minus some number divided by 10. Does that equal leap? But the exact same premise, and unsurprisingly, since angr is powered by Z3, it has absolutely no trouble dealing with this. And actually, I can just run medium solve here and give it a second. And I haven't compiled it, have I? Now that I've compiled it, you got to give it a few seconds here. There we go. And I think if we give it an input of, let's see, we want to run medium with 7318. Oh, actually, it's in here. There we go. It's correct. So, same idea there. Now, hard.c is kind of an example of where symbolic execution can get difficult. So what it does here is, I wrote this a little bit obtusely, it takes your input and for every, so n times for an input of n, it calls WTF with this value thing here. And all that does is it increments the value by 1. Now, this makes things complicated. You remember before we had 2 paths, right? Well, now we got at least 10. So we have all these different possible paths, like everything with 1, 2, 3, 4. Every single possible numeric input is a different path, a completely different program trace. So we have to explore, if the target number is 10, then it's going to probably wind up counting from 0 to 10. If it's 13,037, we got over 1,000 paths to explore. This made my computer very unhappy. So symbolic execution can get frustrated by these path explosions, as they're called. And these can become exponential. So, for example, this was at least linear because all it really was is either you take the loop or you exit. If you have something that's a little, weirder, like, you have 10 sequential if-else things that all kind of nest inside of each other, or, a recursive function that's calling, one of two other recursive functions 10 times, you get 2 to the 10 paths. So you can get thousands or millions of paths, which will very quickly overwhelm your, symbolic execution engine. So dealing with this is the tough part of symbolic execution. There's a lot of things you can do here. You could try to only explore little bits at a time, maybe even, simplify and kind of just cut out unwanted paths. Like, for example, you could recognize, okay, this is just incrementing another number. So I'm just going to, replace that with an assignment, and then it's trivial. Or even things like symbolic execution, where you're kind of mixing symbolic and concrete execution, which is what things like, I think the driller symbolic execution engine, or the driller fuzzer, uses a mixture of concrete and symbolic execution to find and explore interesting program paths. And we might actually talk about fuzzing a little more sometime in the future, so stay tuned for that. But yeah, symbolic execution can get very badly mangled by these kind of path explosions, and generally things that result in a lot of busy work for it will cause major problems. Like, for example, another interesting example is like a program that it calls rand, and if the result is 0, it does a really expensive operation. Well, the symbolic execution engine doesn't understand that rand will almost never return 0, and it's probably irrelevant. It'll see two paths. Either rand was 0 or it wasn't. And therefore, it's going to check both sides. And then the left side will be this massively expensive operation. Everything gets stuck. It's terrible. So there's a lot of interesting attacks in symbolic, analysis. And, the real meat, I think, of symbolic execution is getting around that and, you know, figuring out how to, overcome those kind of obnoxiously designed programs. So yeah, that'll wrap things up for today. Pretty quick. We didn't get too far into the weeds with this one because it can get very kind of overwhelming very quickly. If you're interested in more of this, I would highly suggest checking out Angr's documentation. You'll find kind of demos, tutorials, things like different ways to explore the program, so you can try to avoid those kind of pitfalls, those bad paths, as well as things like all the different ways to actually search for things, like like you can target specific instructions, you can target specific outputs, that kind of thing. Definitely check that out if you're interested. And so keep an eye out, because next week, as I mentioned, we're not having talks, Thanksgiving break. The week after that, we'll be continuing, and our current plan is for some fun embedded hardware stuff. No promises just yet, but it's on the table. So if you'd like to keep informed, stay up to date, I suggest join us in Slack, rpsect.slack.com, as usual. And if you want to look at the files for today's talk, tools.rps.ec is where you want to be. Check the description, it'll be in there as well. So yeah, that'll wrap things up. Thanks for coming, and we hope to see you again in 2 weeks.